Okay, it's time for another class, another one of these video classes to make up for this time that we can't have together as a normal class. AC/DC circuits. Last week we talked about series inductive resistive circuits. So AC, alternating current circuits with a resistor and an inductor. This week we're going to talk a little bit about that same circuit but with the inductor and the resistor in parallel with each other and in parallel with the voltage source. And there's a slightly different way we go around that circuit. Obviously, we're going to have the differences that we have between any series and parallel circuit. In series, we have a voltage divider, and in series, we have the same current everywhere. On a parallel circuit, we have a current divider. We're going to have different current in each branch, depending on the load of those branches. We're also going to have the same voltage at any items that are in parallel with each other. So since our source is in parallel with our resistor and our inductor, in the simplest circuit we're going to do, we'll know that that same voltage will be seen in each one of those components. The voltage that the source puts on the circuit will be the exact voltage seen by each of those components, since we're modeling our wire as a perfect conductor. A couple of points of business for the class. I have not given you guys a video yet on that quiz that I was supposed to give you not a makeup video, a go-over video. I think that most of you did really well on it. If anybody needs some individual help with anything on the first or second week quiz, let me know and I'm willing to go over that either one-on-one through a video conference or however you'd like to do it. We can do it in a series of emails or texts. Let me know. If we have a quiz that is a big problem for a lot of people, I'll obviously go over that quiz with you guys. But I think everybody did really well in the series. Everyone that I've gotten so far. It is Thursday night as I record this, so I still haven't gotten a few from some of you. Thank you for everybody that's put out the effort to make the Moodle system work and to submit your quizzes as PDFs. It allows me to grade them within the actual software. If you send me a JPEG, sometimes I can't open them at all. I've actually had to get another instructor or somebody at the JTC to try to open up their system, download the JPEG, send me the JPEG, and then I've got to open it up in a different system. If you put a PDF into Moodle and it's the right size, I can open it up right in Moodle, make my comments as I'm grading it for you. And since there are like 50 people in this class now, that helps a lot. Let's go ahead and get to what we're doing this week. And we're going to take it a little further. Last week we went all the way to, in a series circuit, we figured out what the individual voltage drops. And again, we saw last week, if you remember, that there were Pythagorean relationships in the voltage drop in a series circuit, because a series circuit is a voltage divider. This week we're going to see that a parallel circuit, being we already know as a current divider, that the Pythagorean relationship, the right angle relationship between what's going on in the inductive branch and the resistive branch is going to have that same Pythagorean relationship. Voltage is going to be the same everywhere, so there's no change in voltage, so there's no Pythagorean relationship with the voltage, or in that case with the resistances, the ohms values, I shouldn't call them resistances, with the impedances that we're going to see. Resistance being one flavor of impedance, and reactance being the flavor of impedance that we get because of a coil that is receiving a alternating current. Let's go ahead and draw this circuit and talk about it. And I'm just making this up off, again, shooting from the hip on these, just like I do in class. I've got a voltage source. I'm going to go out and just throw the resistor in first. It really doesn't matter which one goes first or which one goes second. It's just like if these were two circuits in a house you were wiring. It doesn't matter if I put the kitchen in the top breaker and the bathroom in the third breaker or the 17th breaker. It's all the same thing. That's essentially what I've got here, is I've got two parallel circuits. And you know, like when we wire a house, everything's in parallel. All the voltages are the same. Every receptacle is going to have 120 volts because we bring a hot and a neutral to every receptacle. Just like we're bringing, if I model this as plus and minus, and again, I always ground that just so I can say it's zero. If I'm modeling it that way, this is like the hot wire. And of course, I brought a hot wire to this load, and this would be like the neutral or the return on a 120. Or it would be the other hot on a 240, again, depending on what kind of circuit we're using. Let's go ahead and keep our numbers really simple. I'm going to say this is a 100-volt source. Now, I don't have to, a lot of you guys answered RMS in your quizzes, and that's fine. Anytime we're talking about AC now, we're going to be dealing in RMS. That is the standard for power circuitry for what we as American electricians do. We measure things in RMS. So from now on, you don't even have to label it RMS. RMS is assumed. Just like, because we're Americans and we're electricians, we are going to assume 60 hertz unless we're told otherwise. So unless you woke up in Germany or in the military, you're going to be at 60 hertz. Let's go ahead and throw some values in these. For the resistor, I don't know, I've been using 50 ohms, I think. And usually when I pull a value out that's in the between 40 and 90 or maybe 120 millihenries, I know at 60 hertz I get a value I can use. And I just know that from experience doing these on the board. So I've been throwing out, just pulling one out of you-know-where. Let's go ahead and do 62 millihenries is going to be my inductance at that coil. Now that inductance is an intrinsic value. It will not change. If I pull that coil out of that circuit and throw it into a DC circuit, I'm still going to have 62 millihenries of inductance. If I pull that circuit out, that coil out of this circuit, throw it into a 400 hertz on a boat or 50 hertz circuit in Germany, it's still going to have 62 millihenries. But the X sub L, the inductive reactance, will change, because the inductive reactance, as we know, is equal to 2 times pi times the frequency, in this case 60, times the inductance. So if I change that 60, I'm going to change that. Let's go ahead and write it up the way we know it, though, is with the F. I always make my F small because I think a frequency is a small F. I see it as a large F in some places. But I think of that as farads, which we're going to talk about later. So 2 pi times frequency times inductance. We do have some other formulas that use the L as length when we do voltage drop formula. But this formula, 2 pi fly, L is the inductance. So if I run that through my calculator, that's the first thing I need to solve in this circuit, because I've got the voltage, I've got the resistance. I mean, I can solve everything in this part of the circuit. At 100 volts, 50 ohms, I'm probably going to have 2 amps running through there, right? Let's go ahead and solve X sub L and then get to the totals. I'm going to get out my calculator. Clear, 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 and I'm going to go 2 pi 60, and that's exactly what I typed in there, 2 pi 60, and then I have to hit the multiply button, because the 2 pi 60 doesn't need that in between them, because the 2 and the pi separates 2 numbers with a symbol, which is also a number, and the calculator didn't notice just to multiply that. 2 pi 60 times, remember that I have got 62 millihenries here. So 62 millihenries equals 0.062 henries. If you watched either of the other videos that I asked you to take a look at of other instructors teaching this, one of them you may notice uses, he'd use 62 times 10 to the negative 3, which is the same thing as 62 milli. If I had 62 kilo something, it would be 62 times 10 to the 3. If I had mega, it would be 62 times 10 to the 6. But we're not going to use that scientific notation. If you're comfortable with it, you can use it. Don't give your answers in that, though. I don't want to have to think that hard. But if you learned that stuff, go for it. So X sub L in this case equals 2 pi 60 times 0.062. Double check my calculator. That equals 23.37. 23.37 ohms. So remember, the value, the unit for any sort of impedance is in ohms. Resistance is in ohms, and inductive reactance is in ohms. So I'm going to label those ohms. Now, so essentially what I've got is I've got 2 individual series circuits that happen to be sharing some wire. I've got this loop or series circuit. I've got this loop or series circuit. Obviously, it's not a series circuit, because if I'm an electron, I get to here, and I can either go this way or I can go this way. So let's go ahead and solve our individual currents in the branches. So I'm going to label those. I'm going to call those I at R, and I'm going to call them I at L. So I at R is the current in the resistor, And I at R is going to equal, let's see, I equals E over R, right? In this case, it's going to be 100 volts over 50 ohms, and that's going to equal 2 amps. So I've got 2 amps flowing there. Boom. 2 amps. Now, for the current at the inductor, my formula is going to be E over, in this case, X sub L. So, because R and X sub L are both flavors of Z, which we've essentially inserted there in our Ohm's law. Ohm's law is still ohms. We named the ohm after, was it George Ohms or Gustav Ohms? I can't remember what his name was. I think it was George. We named that after him, but in this case we're going to use impedance, which is the bigger value. And E X sub L is the flavor impedance here. Still have 100 volts. Remember, that's the rule on parallel circuits, is the voltage across any component is the same as the source voltage when they are in perfect parallel with the source voltage, and those are. So I've got 100 volts here, I've got 100 volts here, I've got 100 volts here. That's the common thing. That's my, well, some of the instructors I've seen call that, that is not our starting point, but our, I can't remember what they call it, 100 volts divided by 60, not 62. Can't divide by my inductance, I have to divide by my X sub L, which is 23.37 ohms. So 100 divided by 23.37, that's going to be 4 something, isn't it? Let's see. 100 divided by 23.37, that equals 4.28. I'm going to round it to, it's 4.2789. So I'm going to get rid of my ground here for a second. 4.28 amps. So not only do I have 2 amps flowing there, but I have 4.28 amps flowing here. Now, this is a current divider. And like I said last week, when we think about the relationship between the current in a current divider, the current in the resistor, and the current in the inductor, we have to remember that they have a 90-degree relationship to each other. This current, this inductor, is producing a back voltage. It's pushing back on the voltage, and therefore the current, because remember, current is just a product of being pushed by the voltage. So that's pushing back on that voltage, and it's changing the current here compared to here. Because it is a current divider, I have a Pythagorean relationship in the current. So in order to figure out what my total current is, what these two currents together add to, I need to do a Pythagorean relationship. So if I was going to graph this thing, and I was going to show those two currents, I could have the current of the one looking like that, probably the current of the resistor, and then remember, this is just representing that rotational force. The reason I have a sine wave is because I generate power with a rotational generator, whether it's a turbine or whether it's a turbine or whether it is a nuclear reactor, which just has a turbine that's powered by steam, or whether it is a I've lost the word for it, getting old, that's tough. It's all rotational, and that rotational movement can be divided up into 360 pieces, and we can go ahead and apply those to the sine wave. So, if that's the case, then I start out here, so t equals 0, but my degrees here is also 0. And when I get to here, I'm at 90 degrees. When I get to here, I'm at 180 degrees. Here is 270, and here is 360. So if I'm at 90 degrees here, and this is the current in my resistor, then I'm probably going to have a current in the inductor that is 90 degrees different. It's going to look just like that. And when I add those two things together, I'll come up with another sine wave altogether. If I, at every point of this sine wave, added, so like at this instant, I added this number and this number, I would come up with a number. It would be pretty close to here at that point, right? If I added this number and this number, I would come up with a number that was pretty close to here. If I added these two numbers, it would be higher still. So my resultant sine wave is going to be something between those two. And there's a way we can measure that, and we're going to get all the way there tonight. But understand for now that because I've got one current at a particular sine wave here, I've got another current at a particular sine wave here, we can add those two sine waves together to get a third sine wave. And it will be a third sine wave that we see from that. That's what we're going to have right here. And here's a way we can figure that out right now. It's the Pythagorean relationship between those two. So again, currents is what I'm dealing with here because it is a current divider. And I'm going to go ahead and put in some numbers here. So my current at the resistor is 2 amps. My current at the inductor is 4.28 amps. Go ahead and figure out what my hypotenuse is, because again, the hypotenuse is going to be the resultant vector of these two vectors at 90 degrees from each other. We're actually solving for this, once again, by solving the hypotenuse. And I do that hypotenuse, which in this case is going to be I total equals the square root of I at the R plus I squared at the L squared. IR squared plus IL squared. The current at the resistor squared plus the current at the inductor squared, their square root. So again, I'm going to dump that in my calculator. Clear, clear, clear. I'm going to say 2 squared plus 4.28 squared equals some other number, second square root, second answer. Enter that, and I'm going to get 4.724. 4.724 amps. Think about my unit there for a second, what we're talking about. So, does that number make sense? Yes, it does. It is more than either of the two sides, and it is less than the two sides added together. If it was more than 6.28, I'd say that's not a legitimate triangle. If it was less than 4.28, I would say that's not a legitimate triangle. But as it is a legitimate triangle, so I can go ahead and use that number as my total current. So I total equals 4.724 amps. And I've essentially solved my currents and my voltages. I didn't have to solve my voltages. My voltages were a given. I figured that out. Now, can I solve Z, my total impedance? Yes, I can just use Ohm's law, because Z equals E over I. And I know that my E is 100 volts, and I know I've just solved my I for 4.724 amps. What is 100? Clear. 100 divided by 4.724 equals, and I get 21.17 essentially ohms. 21.17 ohms is my Z. So, does that number make sense? Well, yes, it does, because remember, anytime I have two branches, and each of those branches has some resistance or impedance in ohms, I know that the resultant of those two together has to be smaller than either one. 21.17 is smaller than the smaller of those two, 23.37. So that makes sense. Anytime I add a branch to a circuit, I'm going to, and that branch has current flowing in it, I'm adding current to the total circuit. If I've added current to the total circuit, I have decreased total impedance, because the two are inverts of each other. In order for one to go up, the other must go down. It's doing the same thing. If I decrease my total impedance, I'm increasing my current, and vice versa. So that makes sense. Let's go ahead. The book, actually, I wanted to say, and I said this a little bit, the book has given you a bunch of other formulas for this, because not only do these two things have a reciprocal relationship, just like we learned in resistors, 1 over R plus 1 over R, and then invert that, but it also has a Pythagorean relationship, which we just talked about. So the book is going to tell you about Z equals 1 over the square root of 1 over R squared plus 1 over x sub L squared, each of those in parens. That's a difficult formula to run into your calculator and get correctly, and honestly there's no real reason for us as electricians to know that. It's great to understand that that happens. What this formula is a mashup of the two formulas that are going on here. It's the invert formula and it's the Pythagorean formula. You can see Pythagorean here, square root of two things squared, but then it inverts both of them also to get that reciprocal formula. So that's a mashup of those two formulas, and it works. But I suggest that unless you're a math whiz, that you stay away from that. Instead, we solve this thing with Ohm's law. We stick to the most complicated thing we do is the Pythagorean relationship, because we can see those and understand where they are and why, and we get there. Later, when we add a capacitor to this in parallel, there's an even uglier, bigger formula that they're going to show you that you can use to solve Z. Again, I suggest you use Ohm's law to solve Z, and you do it after you've solved for voltage and for current. And that works just great. Oh, let's go on and erase a little bit of this. I think I've got everything I need all the way to here. I'm going to leave Z equals 21.17 here. Z equals 21.17 ohms. And I'm going to erase a bunch of this stuff. And we're going to go on and do some things with power. So remember, power anywhere is the current times the voltage. I mean, that's the most basic power formula. I times E. P equals I times E. So if we go ahead and solve that in each of these, we're going to get a couple of powers. Let's go ahead and do that. So let's say power at the resistor, and I'm going to call it P at R for right now, but later I'm going to call it something else, and I'll tell you when I make that shift. Power at the resistor equals I times E, which equals 2 amps times 100 volts, right? I've got 2 amps flowing through the resistor. I've got 100 volts dropping across the resistor. 2 times 100 equals 200 watts. We already learned that, right? That's straightforward. That's exactly the same way we did this in DC circuits. Let's go ahead and do it at the inductor now. So P at the inductor equals I times E, because I've got a current at the inductor and I've got a voltage drop across the inductor, right? The current at my inductor is 4.28 amps times, same thing, 100 volts, and that equals 4.28 watts. Well, it's 4.28, but it's not watts. So this is the funny thing. Now, when we're dealing with impedance, I've got basically 3 flavors of impedance, right? I've got resistance, I've got capacitive reactance, the reactance because of a capacitor and it's it being influenced by an alternating current, and I've got the reactance by an inductor and its influence under an alternating current. But when I've got power, and those are all ohms, when I've got my Z, my X, and my R, we measure them all ohms unit. But in power, for whatever reason, they've decided to say, well, if it's power at an inductive or capacitive, if it's a reactive element, now reactive elements are inductors, are capacitors. Another term I haven't brought up yet, I should probably have addressed last week, nonlinear loads. You guys have all heard of linear and nonlinear loads. Inductors and capacitors are nonlinear loads. And that is because they don't have the same phase in either the voltage or the current, depending on how they're set up, as the source. Whereas resistors are linear loads. So that's a term that we may throw around a little bit. But my nonlinear loads, my reactive elements, we actually do those in VARs. The unit itself is VARs, VARs, or just VAR. And that stands for volt amps reactive. So it's volts times amps reactive, because it's a reactive element. So I've solved this power, and I've solved this power. Now, if this was a DC circuit, or if it was all just resistors in this circuit, I could just add those things up. But guess what? Those two things also have a Pythagorean relationship. And let's go ahead and talk about that Pythagorean relationship and draw our power triangle. The first triangle we did was our current triangle. It was the relationship between the current at the resistor and the current at the inductor and the total current the source sees, and how those things are related. Two different sine waves, we can add two sine waves to get a resultant third sine wave, which will be different than either of the others, and will have some lead or lag from the original sine wave. Just like the sine wave at the inductor is 90 degrees out of phase with the sine wave at the resistor, the resultant sine wave between those two is going to be something between 0 and 90 degrees different than the source sine wave. Well, when we do power, we've got a similar thing going on here. Let's go ahead and roll these the way we do. I'm going to say power at my resistor. Now, I'm going to change that. I'm going to stop. This is that moment I was telling you about. I'm going to stop calling that power at the resistor. I'm going to call that now true power, power T. Don't confuse that as power total. This power total is something else, and we'll talk about that. This is true power, and it is all the power dissipated in the form of heat by a resistor. That's all a resistor does with power, is it creates heat. It takes electrical energy and it turns it into heat energy. It heats something up. That's what a resistor does. The element in your stove is a resistor. The element, obviously, in a cadet heater is a resistor. Almost everything else is going to be an inductor, maybe something's capacitor. Most anything that creates a movement is an inductor, and we'll talk about why that is. Anything that creates heat is a resistor, with some caveats and some hybrid things in between those two. But essentially, if it creates heat, it's true power. It's power that has stopped being electrical energy and turned into heat energy and has left the system. All of this power is power that's now gone away. This power, voltamps reactive, is actually power that gets returned to the system, believe it or not. This thing charges up and pushes back, and at the off cycle of every cycle as it goes up and down, this thing is charging up and then pushing off, charging up and then pushing off the other direction. So a lot of this power that we call power, it's voltamps reactive, is just the source seeing, hey, I've got to supply this many volts to push this many amps through that thing. And this, as far as the source knows, it's doing work. As far as we as electricians know, we got to size that wire big enough to take those amps, and we've got to size the insulation on that wire big enough to take those volts, because you know that's how we size those two things. We size the actual conductor by the amount of current it'll take in our code books, 310, 15, B16, and the insulation is the thing that we size big enough to insulate against breakdown at a high voltage. So most of the wire that you and I are going to work with in our careers has an insulation that's rated at 600 volts. And so we just use it all the same way. Hey, 600 volts, it's good. The highest it's ever going to see is probably 480. We're good to go. Mostly we're going to be working in 120, 240, maybe a little bit of 208 thrown in there, 277. Anyways, for us to size that, we have to take this guy into consideration. Even though the power is being returned to the system, we still need to size the wire for it, and the system still sees that as power it needs to supply. It might get it back, but it needs to supply. It's kind of like the electrons. The electrons go out, they do their work, but they come back, right? So the power company at the end of the day isn't out any electrons, right? They got every electron they started with. The electrons all just live in the conductors, right? But they provided the energy that pushes those electrons. And whether they push the electrons to come back into the system or push the electrons into a resistor that creates heat, either way, it costs them. So anyways, our unit here is VARs, and we're going to put the VARs over here. We're going to say, and it's not 4.28 VARs, it's 428 VARs. Excuse me if I made a decimal error all the way around. 4.28 times 100 volts is 428 VARs. I'm going to put those over here, VARs, on our power triangle, and I'm going to put my 200 watts here. Now, obviously, we're going to figure out what our hypotenuse is. And our hypotenuse is going to be what, if you didn't know better, you might call total power. But it's actually something we call apparent power. Power apparent. And power apparent has a third unit. It's not watts and it's not VARs,